This is Secondary 2 Honors Math. This is Lesson 2.4, and we're going to be learning about right triangles and the geometric mean. We're going to start off just reminding ourselves about a right triangle. So a right triangle because it has a right angle. In a right triangle, we have the sides, and they are identified as legs, and a hypotenuse. The hypotenuse is the side opposite the 90-degree angle. The legs are the shorter two sides. Okay, the first thing we're going to do is we're going to talk about the similarity of these triangles. So if you look at this picture, this is something we're going to see a lot of diagrams that are going to look similar to that. And so to start out, we're going to make sure that we establish what we're working with here. So I've got three triangles. I have got this large triangle, which is, we'll call it ACB. And when I look at that triangle, notice like where it begins and ends and the angles and everything. Okay, now I've got the small triangle. I'm going to call that, let's see, I got to make sure everything's going right. So we're going to go, we did ACB, so we're going to say ADC. So those two triangles right there, if you just look at those two, notice that they both include this angle, angle A, and they both have a right angle. So because they both have, or they have two angles the same, the third angle would then have to be the same also. And if two triangles have the same angle measurements, they are going to be similar. One is a dilation of another. So we have two similar triangles here. So we can say that since angle A is congruent to angle A, that's reflexive property, and angle in the small triangle, its angle ADC is congruent to, in the large triangle, the right angle is ACB, and that's because right angles are congruent. So because of that, triangle ACB is, not congruent, similar to triangle ADC because of angle-angle similarity. Okay, so we've proven that those two are similar. So I'm going to now take another approach, and let me erase those colors, and let's take a look at some other triangles. So let's still keep ACB, so that one, so triangle ACB, and then let's look at this other triangle, the larger one right there, and so it's right angles right there, so I'm going to say triangle CDB. So I'm going along the short leg first. I'm trying to prove that they're similar. Going along the short leg first of both of them, and then going to the right angle, so that's how I'm going to line it up. So if you look at the red triangle, red and purple, they both have a 90-degree angle, and notice that both of them include angle B. So it's just like the one that we just did, so angle B is congruent to itself, and then angle CDB is congruent to angle ACB, because again, right angles are congruent, and so we know that ACB is similar to CDB. So I'm going to box that in right there, box this one in. Now if ACB is similar to both of those, then these have to be similar to each other as well. So we've got three triangles that are similar to each other within this one picture. So all three of these triangles are similar to each other. Now if triangles are similar, then the ratio of their sides is equal in proportion. So let's write some ratios about the sides. So I'm going to take the smaller triangle right there, and I'm going to say that the short side of that triangle compared to the hypotenuse is going to be equal to the short side of this triangle and the hypotenuse, and it's going to be equal to the short side and the hypotenuse of that triangle, so CD over CB. So that's this string of proportions where all of those things are equal. Now I can continue and write other proportions for the rest of those comparisons. Oh, whoops, sorry, back here. If I did the short side, that should be AD on top. AD, that was the short side, and then the hypotenuse, AC. Now I can write similar strings of proportions for the other comparisons. So again, if I take the small triangle and let's do one we didn't do, so let's do the longer side to the hypotenuse, and then get the larger triangle and do the medium side to the hypotenuse, and then get the medium-sized triangle and do the larger side to the hypotenuse. I've got another string of proportions. And then I can do the other ratio as well. I'll just go ahead and put that one up. Remember, when you're writing ratios, if I was to do these the other way around, so AC over CD, that would be fine as long as I swapped all of those, so it's not going to matter as far as that goes. But I just have this set of proportions to look at. So the other one that I'm going to write is going to be AD over CD is equal to CD over BD, which is equal to AC over CB. And so all of these are true because of the similar triangles. And so keep that in mind, because on your homework you can use that to prove the Pythagorean Theorem. And you might need to look at the answer key to help you along with that, but I want you to understand how it's working. But see if you can do any of it yourself. But if you need to look at the answer key, I can understand that it's a little bit hard to do, but you can prove the Pythagorean Theorem that way. Now, last year we used the Pythagorean Theorem and we saw a proof of this. Okay, when you do it visually like that, so you have this square, well, you've got a triangle, so side A, B, and C, and you can make a side that's C by C, and then a side that's B by B, and that's the purple, and then a side that's A by A, and then you can rearrange those pieces. And so you can prove that A squared plus B squared, which is the red plus the purple, is equal to the blue. We saw that last year, but anyway, this is just another way to prove the Pythagorean Theorem that you're going to do in your homework. So let's just use the Pythagorean Theorem. You've done this before, so just quick review. You can just go ahead and pause this, work it out, just make sure that you remember how to do it. Okay, there's number one. So it helps speed things along because we know square numbers quickly. 194, you know it's not a perfect square, so you're going to write the square root of 194. Remember that that's exact. And then if you round it, it's going to be approximately 13.9. So it's just going to depend on the directions, which one of those that you're going to do. Number two, e squared plus 12 squared equals 20 squared. So again, it speeds us up because we know this. You end up getting 256, which you know is a perfect square. The square root of it is 16, so this is exactly 16 units. Okay, so next thing is we're going to review arithmetic mean. So you guys learned this a long time ago. It's also known as the average. And so if you're finding the mean value of a series of numbers arithmetically, you would add them together and divide by however many numbers you have. So if you're finding the average of 5, 9, 8, and 16, you would add them all together and divide by 4. And so you've done that before. So we're going to look at something else. This is called a geometric mean. So since with arithmetic mean, you add and then divide, we're going to do something different with geometric mean. To find the geometric mean, you multiply and then take the square root. So to find the geometric mean of 9 and 16, you're going to multiply 9 times 16 and take the square root of that. Now you can do this without a calculator because that's the same thing as the square root of 9 times the square root of 16, which is 3 times 4. So the geometric mean is 12. So let's practice just finding the geometric mean. So 12 and 18, you're going to do 12 times 18 and then take the square root of that. And so you can calculate that out. That's going to be square root of 216. 216 is not a perfect square. It is a perfect cube, so 6 times 6 times 6, so it's going to be 6 square root 6. And so this is the geometric mean. 10 and 40, we're going to take the square root of 10 times 40, which is 400. You know the square root of that is 20. And the square root of 45 times 80. And so you can work that out, break it down however you will, and it's going to be the square root of 3600. Now you know that that's the square root of 36 times the square root of 100, so that's 6 times 10, so that's going to be 60. So that's just using the geometric mean in theory, so what is it for? The geometric mean has applications in our geometry, so we can use similar triangles and proportions, and we can prove that this works, but we can use it to find the missing pieces in a right triangle. So if we have a triangle that looks like this, notice how that looks the same as this does right here as far as how it's divided. So you've got this segment that's coming down from this right angle straight down to the hypotenuse at a right angle. So if you see something like that, then the geometric mean is now something that we can use to find the missing piece. So how can you find that? Well, x is going to be equal to the geometric mean of the pieces of the hypotenuse. And so when you have a picture like this segment that comes down, if you take x, it's going to equal the square root of 3 times 6. And so that's the square root of 18, which is going to be 3 square root 2. And so easily we can find it with that. Now you might look at that and say, okay, what? Why does that happen? So it all comes back to these series of proportions. If you look at these proportions, and we just took a couple of them, we could say that CD, is that equal to AD times DB, and you take the square root? So let's take a look. So using those pieces that I just said, it looks like this is going to be what I'm going to use. So if you look at AD over CD equals CD over BD, if you do your cross products, you're going to have CD squared equals AD times BD. So take the square root of both sides. So CD is equal to the square root of AD times BD. And so that's why we can use the geometric mean. So that's just a good way to do it. Now, there's other ways you can do this. You can struggle around with some other things. Depending on what information you have, you might be able to find some other pieces. But in this picture, this is really the very best way to find a missing piece. So let's take a look at this one. We notice that from the right angle, we have drawn this segment at 90 degrees. I know that this one's 20, and then my pieces are x and 12. So I would say 20 is equal to the square root of x times 12. Now to solve that for x, what we're going to need to do is we're going to square both sides to get rid of the radical. So 400 equals 12x. Divide by 12, and you're going to get, you can do, let's see, as nearest tenth. Oh, simplified radicals and as a decimal to the nearest tenth. So I know that I can put that in my calculator. It's going to be 33.3 repeating. And the square root, or the radical for that, there is no radical for that. So that's how that's going to be. 100 thirds would also be acceptable. Usually when we're talking about the length of something, we usually would say 33.3 instead of saying 100 thirds. So that's what I would say for that one. The next one, you notice we're given different information. So this one I don't have, so that's a question mark, but I need to find this one. So that's different. Now if you think about it, you might think, well, can I use the Pythagorean Theorem? Well, this is 4, and then I don't know this one either, so I can't use the Pythagorean Theorem for that. So that's a no. I know that this one's 3, since the whole thing is 4, and I know this piece is 1. But if you look at everything, I just don't have enough information to find all of the other missing pieces. Like, I couldn't find that if I looked at this triangle. I've got 2 unknowns. If I look at this triangle, I've got 2 unknowns. I just have too many things I don't know. And so the geometric mean is what's going to allow us to do this. So the first thing I'm going to do is I'm going to find that piece right there. Sometimes you have to find something extra to get to where you want to be. So that's going to be square root of 3. So I'm going to put square root of 3 right there. And now using that, let's take a look at this triangle. So I'd say 1 squared plus square root 3 squared equals x squared. So Pythagorean Theorem. So 1 plus 3 equals x squared. So that's 4 equals x squared. So that means x is equal to 2. And so I was able to find that nicely, even though I had some missing parts that otherwise I wouldn't have known how to deal with that. Okay, go ahead and pause the video and see if you can solve these problems. So number 7 is a lot like the one we just did. Number 8, you have to find 3 different values. And so you have to decide which one you're going to find first and how you're going to do that. There's some different strategies that you could employ, so you can decide how to do that. For number 7, x is equal to the square root of 14. So if you did not get that answer, then pause the video and study what I did so that you can compare it to what you did. If you write that as a decimal, it would be approximately 3.7. I chose in number 8 to do y first because I saw that I could easily do this with Pythagorean Theorem, so I chose to do that one first. So I got y is equal to 40. Next, I chose to find x, and I did that using the geometric mean. So I said 32 squared equals 24, 32 is equal to the square root of 24 times x. By the way, that would be the same thing as saying 32 squared is equal to 24 squared plus x squared, and then taking the square root of both sides. So you have 32 is equal to the square root of the 24 squared plus x squared. So that's the same strategy. For z, I'm going to employ a calculator on this one for sure. So I'm going to do 128 thirds, and I'm going to square that, add it to 32 squared, and that will be z squared, so I'll take the square root of the whole thing. When I get done, z is going to equal approximately, well, it's 160 over 3 if you do that. The decimal for that then would be 53.3 repeating. Okay, number 9, you have to find 3 things again. So again, just choose which way you want to go about that, what you think is the easiest to do first. You might do something different than somebody else, that's okay. Go ahead and pause the video, see how you do. Okay, I chose to do z first, and so I got z is equal to 4 square root 2, and so that's how I did that. I'm going to now erase that work so I can show you the other ones. To find x, that's this whole entire piece, and so I don't have enough information right now to do that, so I'm just going to call this little piece of it w from here to here, and I'm going to do that. So if I do this squared, it's equal to 2 times w. That's exactly the same thing as saying 4 square root 2 is equal to the square root of 2 times w. And I'm starting to think that on a previous problem I had said plus, and that's not right. It should be multiply. So anyway, we're going to square both sides. Puts us right back to where we were, right up there. So I'm going to have 2w is equal to 32, and so w is equal to 16. And so if I say that this piece right here is 16, that would make x equal to 18. Okay, last, to find y, I'm going to just use the Pythagorean theorem and say 6 squared plus y squared equals 18 squared. So I'm going to have y squared is equal to 324 minus 36. And so y squared, and so I can simplify that radical. And so I'm going to get y is equal to, it comes out to be 2 square root 2. And so that's how you do that. So this is how you use geometric mean to find missing parts. Like I said, there's other ways that you could employ to find these missing parts. You might choose to do this in a different order. Probably shouldn't have erased that answer. Do it in a different order. You could use proportions and similar triangles to do it. I feel like geometric mean is a really good tool to use, and in something like this, I feel like it's easier to do. You could, say this is the shorter side, and I'm going to compare it to z, which is the longer side, so I could say 2 to z equals, and then if I look at another triangle, I could say the shorter side is 6, and I can compare that to x. The problem is that doesn't help me because I have 2 variables, and so you have to find the one that you only have 1 variable with, and I just feel like that's just a lot to look at. So that's why I like the geometric mean to find pieces like that. Okay, you should be ready to do your homework now. Make sure you pay attention to the directions on rounding or radicals. Make sure you show your work on your paper, and have a great day.